Hello, today we'll be solving the first problem in chapter 20. On his honeymoon, James Joule tested the conversion of mechanical energy into internal energy by measuring temperatures of falling water. If water at the top of the Swiss waterfall has a temperature of 10 degrees Celsius, then falls 50 meters, what maximum temperature at the bottom could Joule expect? He did not succeed in measuring the temperature change, partly because evaporation cooled the falling water and also because the thermometer was not sufficiently sensitive. All right, so what are we given? We're given that the initial temperature is equal to 10 degrees Celsius. And we are also given that height is equal to 50 meters. Now, what equation we'll be using to solve this problem, we will be using the conservation of energy equation. This might sound strange considering that this chapter is on thermodynamics, but remember that the first law of thermodynamics is just a simplified version of the conservation of energy equation. So here we'll be saying delta U, and U here is potential energy, not internal energy, because internal energy is E internal. So as to avoid confusion, because historically the U has been used for both potential energy and internal energy, right? So delta U delta potential energy is equal to Q. Q is the heat. Or we could say, subbing in the formulas, that mgh is equal to mc times delta T, where m is the mass, g is the acceleration due to gravity, h is the height, which we are given, m is again the mass, c is the specific heat, not the speed of light. I know you're thinking that that E equals mc squared right now, and delta T is the change in temperature. Alternatively, we can write this mgh equals mc times T final minus T initial, where T final is what we have to find, the maximum temperature at the bottom, which is where we're measuring it. And Ti we are given, it is 10 degrees Celsius. But before we start subbing in the values, I will just cancel out these m's, these masses, because we do not know them. But we do not need to know them because they cancel out in the math. So again, before we actually sub in the values, let's just simplify this, or actually solve for TF. Firstly, GH divided by C equals TF minus TI. What did I do here? I divide both sides of the equation by C, the specific heat, and then after this we can just add Ti to both sides and we get GH over C plus Ti equals TF. We're given everything except for G, which is, of course, 9.8 meters per second squared. We all learned this, we all know this, we all love this. And the specific heat of water, we can see in this table right here, water at 15 Celsius, but this doesn't really matter. We're just gonna assume that this is the correct value. For 4,186 joules per kilogram times degrees Celsius. 4186, and the units don't matter. So now we just put this into the calculator and see what it gives us. Hopefully it gives us something good. 9.8 times 50, 50 from the H that we were given, plus Ti, wait, no, first we divide by 4186, the specific heat, and then we add 10 degrees from the initial T, and we get this nice little number for TF. Now, I wanted to also highlight something. Why does it say the maximum temperature? It says the maximum temperature because this is an idealized model. As we can see, he did not succeed in measuring the temperature change, partly because evaporation cooled the falling water. So therefore, because we assume that no evaporation occurs, it will be the maximum temperature because nothing is subtracting from the temperature. All right. Hope you found this useful, and until next time.